Hello.
Yes, sir.
Am I audible? Screen is visible to you?
Yes, sir.
Okay. New student. Please, if you have any facility, please share the message. You have to join the control system lecture through calendar only. Because in the Teams, you don't get the link of CS1 lecture at 11 a.m. Join through calendar.
Okay, sir.
Okay. So we just brush up the things that we have discussed in a previous lecture. In the previous lecture, we have finished with the time response determination of second order control system with different values of zeta. Okay. So from last two lectures, we have discussing about this. Okay. So the conclusion is that uh, if you see the time response of second order control system, okay, with different values of zeta. Okay, so time response is nothing but it is a graph of simply t of t versus time t. Okay, so for zeta less than one and greater than zero, we have got the time response plot could be like this. Okay, so therefore this type of response is called as the underdamped type response. Okay, so why it is called underdamped type? Because the oscillations in the response are die out as the time approaches towards infinity. So therefore, such type of response is called as the underdamped type response. Okay, and the values of zeta would be less than 1 and greater than 0 for such type of response. Then second type of response we have seen when zeta is equal to 1. Okay, so for zeta is equal to 1, we got the response like this. Okay, so this is the time response for zeta is equal to 1 and such type of response is called as the critically damp response. Critically damp. Why it is called critically damp? Okay, because the response is close to unity, but never reach to unity. That means it never reach to steady state or the step input. Okay, so therefore this is called critically damped, and this can be obtained when, sorry, zeta is equal to 1. Then for zeta greater than 1, you will get the response like this. Okay, like this. This is for zeta is equal to 1.2, 1.26, like that. So this is called as over-damped type response. Over-damped type response. And this is for zeta greater than 1. And then last step is the zeta is equal to 0. We will get the cosine type response. So therefore, for zeta is equal to 0, you will get the response like this. It consisting of sustained oscillation like this. Okay, so this is the expression for, or the time response for zeta is equal to 0. So in the time response, it consisting of a sustained oscillation. Sustained oscillation. Okay, so for as the zeta value increases from 0 to 1, the oscillations in the system may get damp out, where as again zeta is exceeding 1, so at that time the your time response never reach to unit state. Okay, so these are the certain observations from the time response of second order system when it is subjected to unit step input. Okay, then similarly we can determine the time response of uh, second order system with different input, ramp input, impulse input. Okay, so I have given you the assignment for that. You can try to derive the time response of second order system with subjected to unit step, sorry, subjected to ramp and impulse input. So give the next heading, time response specification. So our next part in the unit number 3 is the time response specification. And we are basically dealing with the time response specification only for the case of under dam type system. So why we are determining time response specification for this case only? Because uh, if you see the properties of time response of second order control system, it is observed that for under dam type system, the oscillations in the system make it damp out. Okay, and then system can reach to steady state. So therefore we want the time response could be of such type. So therefore most of the systems are under damped type. So therefore we are always designing the system such a way that the zeta value should be ranging between 0 and 1. Okay, so for zeta greater than 1, which is not desirable one. Okay, so therefore, it is necessary to study the time response specifications of only under dam type system, because 90% or 99% of the systems are designed having the under dam type response. So therefore, we are simply discussing about the time response specification of under dam type system. Okay, so please, so this is the C of T versus T time response of under dam type system for zeta less than 1. Okay, so please draw this time response, then we can discuss the specific indices of time response specification. Okay, so mainly 3-4 indices will be there, and with the help of that, we can analyze the system with the help of this time response specification. So what is the objective of these performance indices? Okay, so by observing these performance indices, we should know how fast the system move to follow the input. So this is the first performance indices we can determine from the time response specification. Second one is how your system is oscillatory. Okay, so that information we can also determine. And third one is uh, how much time it will take to reach a steady state. So this is the third performance indices. So first type of information we can obtain from the time response specification. Okay. So therefore, I hope you have drawn it. Have you finished this P of T versus T for under damped type system? So with the help of this time response for under damped type system, we can define a time response specification. Okay. So first time response specification we are going to consider is the delay time. Delay time. And delay time is denoted by TD. Okay. So how to determine this delay time TD? Okay. So it is the time required for the response to reach its 50% of the final value in the first attempt is called as the delay time. Okay, so this is your t is equal to 0. Okay, so here and this is the magnitude 1 unit step. Okay, so therefore when your time response reaches to 50% of its value, then the time corresponding to it, it is denoted by td. So therefore let's say this is 50% magnitude. Okay, so therefore the time corresponding to this point is called as the delay point TD. So therefore, we just define the definition of delay time TD. It is the time required for the response to reach 50% of its final value in the first attempt is called as delay time TD. Write down time required for the response to reach 50% of its final value in first attempt okay is called as the delay time td. Then the expression for delay time td, it will be given by 1 plus 0.7 times damping ratio zeta upon omega n. So this is the empirical formula of delay time td. 1 plus 0.7 times zeta upon omega n, where omega is the damped natural, undamped natural frequency. Okay, and zeta is the damping ratio. So this is about delay time. Then second time response specification is the rise time. Rise time. Okay, and it is denoted by TR. Okay, so what is the definition of rise time? Okay, so this rise time can be defined with respect to the type of the system, whether it is overdamp or whether it is underdamp. So for underdamp system, rise time can be defined as it is the time required for the system to reach to 100% of its final value, then it is called as rise time. So therefore, the definition of rise time is we can define like this way. It is the time required for the response to rise from 10% to 90% of its final value for overdamp type system and 0 to 100% of final value for underdamp system. So therefore, rise time is nothing but for underdamp type system. It is the time required for the response to rise from 0 to 100% of its final value is called as rise time. So therefore, here t is equal to 0 and here t is equal to 100. So this is 1 means it is 100%. So therefore, the time corresponding to this time is denoted by TR. So rise time is nothing but it is the time require for the response to reach to rise from 0% to 100% of its final value is called as the rise time. So therefore, time corresponding to this point is nothing but the rise time, and it is denoted by ER. Now, if you want to determine the expression for rise time, because in the many times in the examination, it is necessary to derive the expression for rise time. Okay, so therefore, as we are determining the uh, time response specification for under damped type system, so therefore we can derive the expression for rise time by using the time response of second order under damped type system. So let's derive the expression for rise time. So have you understood what do we mean by rise time? Do you have any doubt in the rise time? So rise time is nothing but what? Simply it is the time required for the response to rise from 0% to 100% of its final value in the first term is called as the rise time. So therefore, TR is the time corresponding to the output of the system when it reaches to 100% of its final value. Okay, so that's why it's denoted by TR. So simply in the time response, instead of T, you just substitute the value of TR, and at that time you will get the output to be unity. Okay, so let's derive the expression for rise time. Okay, so rise time is nothing but it is the time required for the response to reach from 0% to 100% of its final value is called as rise time. Okay, then let what will be the expression for T of T for under damped type system? Can you tell me the expression for zeta less than 1 and greater than 0? For this system, what kind of C of T we have obtained? Can you tell me the expression? Have you remember it? Please tell me the expression. Anybody one? Tell me the value of C of T for under damped type system. Zeta less than 1. What is the expression? C of T we have obtained. Am I audible? Hello?
Yes, sir.
So tell me the value of C of T for zeta less than 1 and greater than 0. We have already derived it, because if you want to determine the expression for rise time, we require that expression. What is C of T? You have not noted down it, I think so. So note down this. Are you noting down, or you are simply listening to me? So step by step you can note down this. Okay. So here we are deriving the expression for rise time TR, and when we get the expression for TR is nothing but the point corresponding to the when your output reaches to 100% of its final value. That means when your output is reaches to unity. Okay, so that time corresponding to that point is nothing but rise time TR. Okay, so therefore, in order to determine expression for TR, we are taking out the time response of under damped type system, and time expression for C of T for under damped type system is given by 1 minus e raised to power minus of zeta omega n t upon square root of 1 minus zeta square into sine of omega dt plus phi. Okay, so give equation number star for this. So this is the expression for time response of under damped type system when zeta is less than 1 and greater than 0. Now, with the use of this expression, we are going to determine the expression for TR. Okay, so how will you determine it? So this is your C of t. So what is the value of C of t at t is equal to TR? So you just substitute simply in the star equation t is equal to TR. Okay, and when you substitute t is equal to TR, what is the magnitude of your output response at t is equal to TR? What is C of t? What is the value of C of TR?
1.
That is 1. Okay, so just substitute C of TR is equal to 1. So that means I can substitute this C of TR is equal to 1. So that means we will get 1 equal to 1 minus e raised to power minus zeta omega n TR upon square root of 1 minus zeta square into sine of omega d TR plus phi. Am I correct? Okay. So you just transfer this one to this side. What will happen? If you transfer this one to this side, so it will be 1 minus 1. Okay. So therefore it could be 0, and which is equal to minus of e raised to power minus of zeta omega n TR upon square root of 1 minus zeta square into sine of omega d TR plus phi. Correct? Then how will you determine the value of TR from this expression? Yes, anybody? What assumptions we have to make in order to determine the value of this TR? क्या करना पड़ेगा TR डिटरमाइन करने के लिए? So the time corresponding to this TR, when you substitute TR, it consisting of two terms. Okay, your first term is this exponential term, and second term is this sinusoidal term. Okay, so if you consider this first term, that is e raised to power minus zeta omega n TR upon square root of 1 minus zeta square. Okay, so this term is, the value of this term is finite for the given value of TR, because it is exponentially decaying, and at the value of TR, this value is always finite. Am I correct? Okay, so therefore we consider as e raised to power minus zeta omega and TR upon square root of 1 minus zeta square is finite. Okay, then what is your second term? Because both the terms are multiplication of each other. This exponential term multiplied by this sine term. Okay, so therefore the second term we are going to consider sine of omega t TR plus phi, and we have to equate this term to 0. But when this term goes to 0, because your first term is finite, but second term, when this second term is going to 0, so for that purpose we are going to use certain assumptions. So let second term is your sine of omega d TR plus phi. Okay, and when this term is and which is equal to 0. Okay, so when this equation is satisfied, when we say that sine of omega d TR equal to 0, when this equation gets satisfied, so write down, the equation is satisfied only if, tell me the condition, when this term is equal to 0. Remember your trigonometric formula. What is the value of sin pi? Sin 0, sin pi, sin 2 pi, sin 3 pi, sin 4 pi, all those values could be 0. So that means we say that omega d TR plus phi, that is equated to n pi. So then and then this condition is satisfied. Okay, so therefore we say that uh, this term omega d TR plus phi, which is equal to n pi in general. Okay, and here we are considering n is equal to 1. Okay, so or n varies from 1 to 3. 1, 2, 3. So for n is equal to 1, okay, see this omega d ER plus phi, which is equal to pi. Okay, so when we substitute this term equated to pi, the value of this term, that means this equation becomes satisfied. Okay, so therefore, from this expression, we are going to determine the expression for TR. So therefore, we will get the value of TR. So TR is equal to what? This pi minus of phi, you can transfer to that side. So pi minus phi upon omega d. Okay, so therefore, you just substitute the value of omega d. So it could be pi minus phi upon, what is the value of omega d? Omega d is the damped natural frequency, and damped natural frequency is always determined from the undamped natural frequency. So therefore, omega d will be given by omega n into square root of 1 minus zeta square. So this is your required expression for rise time TR. Okay, so this is a simple derivation of rise time TR. So this is your first time response specification, and this rise time TR is determined from the time response of under damped type system. It will be given by C of t is equal to 1 minus e raised to power minus zeta omega nt upon square root of 1 minus zeta square into sine of omega dt plus phi, where phi will be given by tan inverse of square root of 1 minus zeta square upon zeta. Okay, so this is the first time response specification. Have you understood it? So please note down this. So we are going to discuss second time response specification, that is peak time TP. So second time response specification is peak time. Peak time, and it is denoted by EP. So here we are going to locate this peak time TP in the time response specification. So I can show you. Okay, so if you carefully observe this C of t, okay, so tell me the value of time corresponding to first peak. Here, this is the highest value of the C of t. The point corresponding to the maximum value of your C of t is this. So this is the first peak in your time response specification. Okay, so therefore this is your first peak of your time response. So therefore the time corresponding to the first peak of your time response is denoted by TP. So TP is nothing but the time corresponding to the first peak of your time response, and it is denoted by EP. So therefore, you just write down the definition of peak time. Peak time is nothing but it is the time required for the response to reach the peak of the time response. Is called as the peak time. So write down, it is the time required. It is the time required for the response to reach the peak of the time response peak of time response first peak. Okay, it is called as the peak time and it is denoted by TP. So now our next task is to derive the expression for TP. Okay, so how will you derive it? Can you tell me the procedure? What we have to do? So जैसे हमने previous case में in the place of T we have substituted TR. So similarly here in the place of T we are going to substitute T is equal to TP. Okay, and with the help of that we are going to derive it. Let's derive this. So again start with the C of T. What is the value of C of T? 1 minus e raised to power minus zeta omega n T upon square root of 1 minus zeta square into sine of omega dtr plus phi. Okay, so this is our equation number star. This is the time response of second order control system. Okay, so in order to obtain the value of time corresponding to the first peak, okay, so what we have to do? How will you get the value of TP? क्या करना पड़ेगा? What is the value of slope corresponding to this point? Yes, anybody? At T is equal to TP, ये जो पॉइंट है आपको टाइम रिस्पांस में मिला हुआ, तो व्हाट इज द वैल्यू ऑफ स्लोप एट दिस पॉइंट? The slope of the time response becomes 0 at this peak point. Am I correct? So therefore, what we are doing, we just differentiate this C of T with respect to time T. Okay. तो आपको कैसा पता चलेगा कि T is equal to TP ऑफर हुआ? How will you detect the point corresponding to T is equal to TP? क्योंकि आपको TP फाइंड करना है, तो आप ग्रेजुअली 0 से मूव करो. Okay, then how will you identify the point corresponding to T is equal to TP? What is the property of your time response at this point? Okay, so what is your observation at corresponding to this peak? Your first derivative of your output response becomes 0 because it is a peak time. So therefore, so you just differentiate your C of T with respect to dt. So dC of T upon dt becomes 0 at T is equal to TP. Okay, so therefore with the help of that we can easily determine the expression for TP. Is it clear to everybody? बाकी इसमें कुछ नहीं है. Okay, so with the help of this fact you can derive it. So at T is equal to TP, we are just simply substituting DC. We are determining dC of T of dt must be equal to 0. Then when it become equated to 0, we will get the value of t is equal to Tp. Okay. So differentiate this C of t with respect to dt and equated it to 0. Okay. So tell me the differentiation of this equation star. What is the derivative of this term with respect to time t, dc t of t dt? To determine dc of t upon dt equal to, what is the derivative of constant term? What will the derivative of constant term?
0.
0. So it is 0 minus, what will be the derivative of this term? E raised to power minus zeta omega nt upon square root of 1 minus zeta square into sine of omega d tr plus phi. So which formula is applicable here? So here you just apply u into v rule. U into v. So what is that rule? V into du plus u into dv. So you just apply this rule. Okay, you will get the derivative of this term. Okay, or simply you just v into u dash plus u into v dash. U is denoted by single dash also. Clear? So let's derive it. So here what is v? So here we are considering v is our we are considering here sine of omega dt plus phi. Okay, so this term v is nothing but sine omega dt plus phi, and u we are considering e raised to power minus zeta omega nt upon square root of 1 minus zeta square. These are our u and v terms. Okay, so therefore let's apply that rule, u into v. So therefore v term is first. So here v term is sine of omega dt plus phi as it is into derivative of u term. So what will be the derivative of this? What is du? Du क्या आएगा? You just apply the chain rule here. E raised to power minus zeta omega nt. So it could be minus of zeta omega n into e raised to power minus zeta omega nt upon square root of 1 minus zeta square. So this is the derivative. So therefore it could be minus of zeta omega n into e raised to power minus zeta omega nt upon square root of 1 minus zeta square. So this is the first term. So here first term we have finished. Okay. Then tell me the next step. Plus u as it is. So u term is what? E raised to power minus zeta omega nt upon square root of 1 minus zeta square. Then tell me the value of v dash. What is the derivative of this term? Sine of omega dt plus phi. So derivative of sine term is, what is the derivative of sine term? Yes. What is the
cos
derivative of sin omega omega dt plus phi? Cos of
omega dt plus phi into omega d.
yes omega dt plus phi into omega d. Am I correct? So this is your dc of t upon dt, okay, and which is equated to 0 because at t is equal to tp, its value is always 0. Okay, so therefore we have equated this term is equal to 0. Okay, so now you just simplify this term. So after this term, please note down this and simplify it. Here is 0, so 0 if you transfer, so it could be become a minus term. So therefore, from these two terms, what is your observation? You just take down the common term, this e raised to power minus zeta omega nt upon square root of 1 minus zeta square. So these terms are common in both the terms. So therefore, we just take down common. Okay, so here is minus. We are taking this term common e raised to power minus zeta omega nt upon square root of 1 minus zeta square. So this term we have taken out common. What is remaining term? Here sin omega dt plus phi. Sin of omega dt plus phi multiplied by minus zeta omega n into minus zeta omega n. Okay, तो फर्स्ट टर्म इज और सेकंड टर्म में बचेगा आपका प्लस ये टर्म कॉमन ले लिया तो ये बचेगा खाली ओमेगा डी इंटू कॉस ऑफ ओमेगा डी टी प्लस फाइव कॉस ऑफ ओमेगा डी टी प्लस फाइव. ओके, तो यहाँ पर आपका ब्रैकेट क्लोज. और then I will simplify this again. So if you multiply this minus sign by whole bracket, what we are getting? So here we are getting e raised to power minus zeta omega nt upon square root of 1 minus zeta square. If you multiply by minus sign, so this minus and this minus become plus, and this plus and this minus become minus. So therefore, ये आपको मिल जाएगा minus of omega d into cos of omega t e plus phi plus zeta omega n into sin of omega dt plus phi. Okay, so after multiplying with minus sign, you will get this. Now again, you can simplify this. So here, e raised to power minus zeta omega nt upon square root of 1 minus zeta square in bracket. Okay, how will you simplify this? You just apply the trigonometric term. So again, it consisting of two terms. This will be your first term, exponential term, and second term consisting of cosine and sine term. So exponential term at t is equal to tp, again it is finite. Okay, so therefore we can write down here at t is equal to tp, the exponential term is finite. The value of exponential term is finite. Okay, then what about this second term, cosine and sine term? Okay, so second term कौन सी है आपके पास में? Here zeta omega n into sin of omega dt plus phi minus omega d cos of omega dt plus phi. Okay, so therefore second term we have theta omega n sine of omega dt plus phi minus omega d into cos of omega dt plus phi, which is equal to 0. Now, when this term is equated to 0, then this condition is satisfied. Okay, but so and here we have derived the expression for time response of second order system. So at that time we have made one assumption. What is the value of zeta? What substitution we have made? Zeta is equal to cos phi, if you remember, and square root of 1 minus zeta square. Square root of 1 minus zeta square is equal to sin phi. So these are the two substitution we have made, if you remember. When they are deriving this expression C of t 1 minus e raised to power zeta omega nt upon square root of 1 minus zeta square into sine of omega dt plus phi. At that time we have substituted these two terms. Okay. So now if you substitute this term, so zeta is equal to cos phi. Okay. So therefore here cos phi into omega n omega n. Don't okay. So here one more modification you can do here. Here we have taken out the term minus zeta omega nt upon square root of 1 minus zeta square. So you just take out the term common, that is omega n into this term. So how will you take omega n common? Okay. So this omega n is omega d is equal to what? Here you just substitute omega n into square root of 1 minus zeta square. Okay, so if you substitute this term omega d by omega n into square root of 1 minus zeta square, so what term we have taken out common? We have taken out omega n into this term. Okay, so therefore इसमें से ये omega n चला जाएगा. यहाँ पर already omega n है, so ये omega n निकल जाएगा. We just do this modification because we have now substituted the value of omega d here. Okay, so we just substitute the value of omega d by omega n into this, and then take out the common term omega n into e raised to power minus zeta omega nt upon square root of 1 minus zeta square. So if you take it common, what is remaining? ये ओमेगा डी निकल जाएगा, यहाँ पर बचेगा स्क्वायर रूट ऑफ 1 माइनस जीटा स्क्वायर इनटू कॉस ऑफ ओमेगा dt प्लस थीटा. सो दैट मींस यहाँ पर ओमेगा डी के जगह आएगा स्क्वायर रूट ऑफ 1 माइनस जीटा स्क्वायर जीटा स्क्वायर. ओके, यहाँ का ओमेगा एन निकल जाएगा, यहाँ पर बचे सिंपली जीटा इंटू साइन ऑफ ओमेगा dt प्लस फाइव. सो नाउ इट इज करेक्ट, जीटा इंटू साइन ओमेगा dt प्लस फाइव. नाउ यू जस्ट सब्स्टिट्यूट दिस सब्स्टिट्यूशन. So 1 minus zeta square is substituted by sin phi. Okay, so sin phi into cos of omega dt plus phi. ये टर्म आ जाएगा जीटा इज इक्वल टू cos phi, तो प्लस cos phi into sin of omega dt plus phi, which is equal to 0. So now what is your observation from this? इसको क्या सब्स्टिट्यूट कर सकते? ये यहाँ पर कौन सा फार्मूला एप्लीकेबल है? साइन ए कॉस बी plus cos A sin B. So it is the formula of what? Sin A minus B. Okay, so therefore here you are getting the term like this, sine of, so we can simplify this equation like this, sine of omega dt plus phi minus phi sin A minus B, which is equal to 0. So this phi get cancelled. So here you are getting simply sine of omega dt, which is equal to 0. Okay, so therefore now you can simplify this. So at t is equal to Tp we have obtained. So therefore we can substitute this t is equal to Tp. So therefore sine of omega dTp, which is equal to 0. So again omega d value you can substitute. Okay, so when this condition is satisfied, sine omega d Tp equal to 0. Again you can apply the formula of when omega d Tp is equal to 0, pi, 2 pi, 3 pi, and so on. So therefore omega d Tp is equal to pi. Okay, so when we substitute n is equal to 1, omega d Tp is equal to pi. Okay, so therefore you will get the value of Tp is equal to pi by omega d. Okay, or you just substitute the value of omega d. So therefore Tp is equal to pi upon omega n into square root of 1 minus zeta square. So this is your required expression of Tp. Okay, so this is your second time response specification. In third, only 2 time response specifications are remaining that we are going to discuss in next lecture. Okay, so today we stop here. So before discussing with, we have 8-minute time. So we are just defining it, which are those time response specifications. So this is about Tp. So do you have any doubt in the derivation? So derivations are quite simple. Okay. तो ये हो गया आपका सेकंड टाइम रिस्पांस स्पेसिफिकेशन टीपी. थर्ड है आपका परसेंट एमपी, और विच इज ऑल्सो कॉल्ड एज पीक ओवरशूट. ओके, so you just give the heading peak. What do you mean by peak overshoot? Okay, so how will you determine it? Okay, so peak overshoot is denoted by MP. So whatever is your first peak and your 100% of output is this. Okay, so therefore the difference between them, the normalized difference between 100% output and the first peak is denoted by MP. Okay, so this difference is called as MP. Okay, sometimes it may express in percent, so sometimes it may express by percent MPL. So this is your third time response specification, that is peak overshoot, and it is denoted by MP. Okay. So again in the next lecture we are going to derive the expression for peak overshoot. So write down next specification, that is peak overshoot. And it is denoted by MP. So you just denote your MP in the time response specification, then write down the difference. So how, if you want to determine peak overshoot, what is it? How will you derive the formula of MP? MP is nothing but simply it is the difference between the first peak of your time response and the 100% value. So what is the value of time response corresponding to T is equal to TR? It is 1. Okay, and here is your C of TP. So that means as you get the value of Tp, you just substitute the value of Tp in your time response C of Tp. So therefore, MP can be given by MP is nothing but it is the normalized difference between the time response peak and the steady state output. Okay, so therefore, how will you get it? So C of Tp. So here first point, then second point is your steady state response. So it will be given by C of infinity upon C of infinity. So its value is always 1. Okay, so therefore here we are getting MP is equal to C of Tp minus 1 upon, again its value is 1. So therefore it is C of Tp minus 1. That is given by MP. Okay, so therefore write down the definition of MP. So MP is nothing but it is the normalized difference between the time response peak that is C of Tp and the steady state output. Okay, so in this way we can make the definition of peak overshoot from this time response specification. Okay. Then next specification is the settling time. So in the next lecture we are going to derive the expression for this MP. Okay. So you just note down the definition of settling time. So it is denoted by TS. So here we are going to locate this settling time in the diagram. Okay. So what do you mean by settling time? Settling time is the time corresponding to the steady state output. So we have seen that every time response is divided into two types, transient term and the steady state term. Okay, so you see this is the point corresponding to the steady state term. Okay, so beyond this, after this point, your time response may reach to steady state, and before this point, your time response may proceed in the transient term. So therefore, the time corresponding to this point is denoted by TS, and that is called as settling time. Okay, so therefore, settling time is nothing but what? It is the time required for the response to reach and stay within a specified tolerance band. Okay, so generally two types of tolerance bands are used. Let's say, so this is the tolerance band, upper tolerance band, and this is lower tolerance band. Okay, so if your output is lie within these two tolerance band, then it will be acceptable. Okay, so generally this settling time can be defined with respect to 2% tolerance and 5% tolerance. So these are the two tolerances accepted. Okay, so this is denoted by ES. Okay, so you just note down the definition of settling time. Okay, settling time is defined as it is the time required for the response to reach and stay within a specified tolerance band usually could be 2% or it could be 5%. 5% of its final value. So this is the standard definition of settling time. Then we are also going to derive the expression for TS. Okay, so today we stop here. If you have any doubt, please ask me.